Okay, so in this video, we're going to derive from scratch the C4 character table. And so normally how we start out um, with these sort of derivations is we think of a molecule that belongs in the the point group that we're deriving, so the C4 point group. This can be kind of difficult um, for these symmetries that don't have mirror planes, like C4, right? Remember, C4 doesn't have a mirror plane. Here's an example of a molecule with C4 symmetry. But basically, what you know is because any of the Cn point groups, or the Dn's or the Sn's, they're not going to have any uh, mirror planes. So there's no sigma V's, no sigma D's, or sigma H's. So the main symmetry operations are all going to be just related to this principal rotation axis, the C4. And so you don't really, for these, have to envision a molecule. I don't find it helpful to envision a molecule for these point groups that, really don't have that many symmetry operations. So what we can do is pretty quickly write down all the symmetry operations. So of course, we're always going to have identity. We're going to have a C4, that's that principal rotation axis. And then we're going to be able to do a C4 twice. Of course, if we do a C4 twice, C4 is a 90-degree rotation. So if we do that twice, that's equal to a C2, 180-degree rotation. And then we can do a C4 three times, and we can't do a C4 four times, because that's the same thing as identity. It's a 360-degree rotation. So there's no mirror planes, and this isn't a D point group, so it doesn't have any perpendicular C2s, for example. So this is actually it. And so we only have four symmetry operations. And so then we have to figure out what are the different classes. And it turns out for the CN classes, unlike the CMV classes, all of these different operations are in their own class. So I'm going to write on the top left of our character table the point group, which is C4. We're going to write the identity class, which always just contains the identity operation. And then C4 is going to be a class, C2 or C42 you could call it. It's going to be its own class, and C43. Now you may be wondering, how am I supposed to know that these are separate classes? Before we called C4 and C43 when we're talking about like C4V point group, we called C4 and C43. We said, hey, those are in the same class because it doesn't matter. One way we just define the axis as one axis for clockwise rotation, one way for a counterclockwise rotation. Both of these are 90 degrees. And that's true for here, but the difference is there's no operation. So if we define, for example, our z like this, our z always has to be coincident with our principal rotation axis. So we're doing a rotation, a C4, we're talking about C4 across this rotation axis. And we define, let's say, our x like this and our y coming out towards us. Then we might define a C4 would be going x goes to y, and a C4-3, right, would take x all the way into negative y. But if we define our axes differently, remember we can define our x and our y anywhere we want. Just our z has to be the principal rotation axis. If we do that now and we do a C4 in that same direction, y is going to x, but a C4 before, so let's see, y goes to x here, and before here x went to y, and y went to negative x, right? Y is going to negative x. So you can see y is going to different things. And for y to go to negative x in this axis, we would need to do a C3. Sorry, for y to go to x, we'd have to do a C4-3. Yeah. For this axis, a C4 does that, and y going to negative x is a C4-3. So these seem very similar, and they are, if we define these different axes, C4-3 and C4 should do the same thing. The problem is the mathematical rule defining what a class is states that you need to have a symmetry operation that can interconvert the axes of interest that you're talking about, that can interconvert these operations. And there's no way you can get with these four symmetry elements, which are just rotation identity, you can't get from this between the left-handed and right-handed coordinate systems, okay? With C4V, where C4-3 and C4 were in the same class, you could do a mirror plane. There's a mirror plane. C4V has a mirror plane. And the mirror plane flips X and Y, and that gets you from one rotation axis to another, therefore allowing you to put C4 or requiring you to put C4 and C4-3 in the same class. So that's sort of the mathematical, rigorous definition. You need to have a symmetry element that can interconvert two Cartesian coordinate systems in order to evaluate whether or not operations should be in the same class. However, it's just easiest to remember for the CNs characters, if you're in the business of deriving these things, that all the operations are going to be in separate classes. Okay, so once we know that, at this stage we continue with our rules, and our rules would tell us that we have four classes. So we should have gamma 1, gamma 2, gamma 3, and gamma 4. And those are just the temporary names I use when deriving character tables for the irreducible representations. Later on, once we get the irreducible representations, we'll give them Mulliken symbols, the A1s, the B1s, the Bs, whatever that might be, T, D, E, using the Mulliken symbol naming convention. But right now, I just call them gamma 1, gamma 2, gamma 3, gamma 4, because I don't know what they are. And I know that there's going to be four of them because I have four classes. So the character tables are always the same number of rows as columns. The first irreducible representation, the first vector, is always going to be all ones across the board. And very quickly, I could find out maybe what some other reducible representation might look like. And so that is going to be down here. So I can think about what using based on functions, right? So it's useful to evaluate some functions and see how some functions transform in these different symmetries to get some of the different irreducible representations. So let's do that. And I'm going to start with Z. And I'll show you why I'm going to start with Z. Just as a test, or just to show you, right? So we're going to do the identity. We're going to do all these different operations on the Z vector. Well, the Z vector is, if I just draw out an axis system, X, Y, and Z, we're doing a rotation. Our rotations along the Z, remember, that's always has to define. Identity on Z, Z goes to Z. A Z vector goes to Z. So we're asking the question, how does this Z vector transform when we do these four different operations? C4, we're spinning the Z vector along the Z. So Z is also going to go to Z. And so very quickly, you can see also C2, 180 degree. You're holding a piece of string and spinning it along the Z axis. If you're spinning something, something that's in that axis, it's not going to do anything. So all these are going to go to Z. And so your matrix for all these, right, you can write a 1-by-1 matrix that takes Z to Z. You take the trace or the character, the sum across the diagonals of that matrix. The character is going to be 1 for all these. Another way of saying that is the Z function transforms as the totally symmetric irreducible representation, which at this point we're just calling gamma 1. Okay, so let's do x and see what happens. Okay, so I'm going to erase this little red z vector, and now let's put an x vector. So we sort of just went over this when we're talking about classes, but x, when we do the identity of it, x is going to go to x. When we do a C4, and remember hat means operation. When I don't have a hat, it means class. X, if we define it as going in this direction, x is going to spin over into y. And now we have a problem. We immediately see that x cannot be defined in terms of just itself. It relies upon y. And so when we see that, it tells us that x and y are going to transform together, okay? And so I'm going to put down a function, x comma y. I don't know what the characters are yet, but we're going to figure that out. So let's do x and y. So now I got y goes to y with identity. Y, if we rotate that same way, is going to go to negative x, right? So maybe I'll use a different color for the y vector in green, and it would spin and go to negative x if we're going to do a C4. So y goes to negative x. Let's keep going. So the C2, that's the next operation. X is going to spin 180 degrees, go to a negative itself. Same thing with y. And then we have the C4 3 times. X is going to spin into negative y. And y is going to spin into x. And so now we just have to write the 2x2 matrix that take these different transformations. And so we have the identity matrix here because xy goes into xy. We take the trace of that matrix, or the character of that matrix, 1 plus 1 equals 2. And oftentimes we'll write it as chi, the character of the identity, is equal to 2. So over here, I'm going to put a 2. And let's do the same thing for the C4. xy, what matrix takes xy and gives us y negative x? Well, that's going to be zeros on the diagonal, and a 1 and then a negative 1 on the off diagonal. And so when we sum those up, we're going to get that the character of C4 operation is equal to 0 plus 0, which equals to 0. So we can put a 0 here. And then we're going to do this for the C2. Again, we're asking what 2x2 matrix takes xy, this time going to negative x and negative y. That's going to be just the inversion matrix, so negative 1s across the diagonal. And so that goes to negative x, negative y. And so then we look at the character of this, and we're going to say chi, the character of C2, equals negative 1 plus negative 1 equals negative 2. So that's going to get us a negative 2 here. And our last one, xy, is going to go to negative yx. And so that's going to have zeros on the diagonal and negative 1 and 1. If you don't know where this is coming from, you'll have to review matrix multiplication. I have some other videos about that. But here, chi of C4 3 times equals 0 plus 0 equals 0. And so we have our final irreducible representation of being 2, 0, negative 2, 0. And so we have one left to find here. We can do this we have one left. I'll show you why there's one left. It looks like there's 4 in a second. That's coming to the crux of some of the difficulties of deriving these CN character tables. But there's a couple ways we can figure out another one that is going to have 1, all 1s or negative 1s. A lot of times you have a lot of characters that have 1s or negative 1s, symmetric or anti-symmetric. And so there's a couple different ways to do this. One is we know our orthogonality rules. All of our vectors have to be orthogonal. We can check that these vectors are indeed orthogonal. And so we have 1, 1, 1. That's our first vector, or I'm using vector and irreducible representation interchangeably. The irreducible representations are indeed vectors. In this case, they're four-dimensional vectors, right? Because there's four classes. But we can check these to make sure that these two are orthogonal. That means the dot product is 0, and it's the dot product normalized by the number of operations in each class. In this case, we have one operation in each class. So all you have to do is take one of these vectors and times all of them by the number of operations in each class. In this case, it's 1. So technically, we should write multiplying all these by 1 because we have invisible ones here, right, for different operations. But if we take this dot product, we get 1 times 2, let's write it out, plus, right, we multiply each component, 1 times 0 plus 1 times -2 plus 1 times 0, which we have two zeros here, and we have 2 and a -2, so we get 0. So we're good. This dot product is equal to 0, so our vectors are orthogonal. So that's very nice. We can use this orthogonality principle to puzzle out what the other irreducible representation is that contains 1. And so let's go through that. I'm just going to assume for now that this is 1. And I'll show you why that has to be true in a second. But for now, we can think about, okay, if this is 1 and the dot product of gamma 2 with gamma 3 has to be equal to 0, then I'm going to get 1 times 2 here. So I'm going to get a positive value here. And so I know this also has to be positive 1 because that's going to get me a -2, a -2 and a 2. That's going to cancel out. And so if I'm just thinking about this is going to give me 0. So if I'm just thinking about gamma 2 dotted with gamma 3, these could be 1s or -1s because this part's going to be 0. But I also have to have gamma 1 being orthogonal with gamma 2. All the dot products have to be orthogonal. And the only way to do that is if I have -1s here. Because I'm going to get a positive 1 here when I go 1 times 1, and a positive 1 here when I get 1 times 1. That's going to give me 2. So I need a -2 to cancel that out. And so that's the only way to do that. We get a -1 here, -1 times -1, and -1 times -1. So that's going to be one way we can figure out what that irreducible representation is. Another way we can do it is by just thinking about what another function might be that's useful. And this function, if you look at this, is actually going to be xy. Because if I have xy, right, xy here is going to go to x times y. That's going to get me a 1. If I do xy here, the function xy, I'll prove it to you right now, that's going to get me y times -x, which is equal to -xy. So just write it out. It's going to get, this is for C4 operation. It's going to get me y times -x, because x went to y went to -x, which is equal to -xy. Well, something just went to the negative of itself. We put down a -1. So 1 by 1 matrix with -1 that describes this transformation. And then here we have a C2. It's going to be xy. For our C2, it's going to be xy goes to -y times -x, which is just equal to xy. So 1 to itself. So we put a 1. And then our last one, C4(3), it's very similar to C4. Xy is going to go to -y times x, which is just -xy. So we have a -1. So at this point, it appears that we are done. And so we can actually go and do our Mulliken symbol. Say what our Mulliken symbol is. And so I'm going to erase these. And there's one small problem. It turns out to be quite a large problem that I'll show you that we're overlooking. But at this point, we can assign our Mulliken symbols. And so while I erase this, I'll just remind you of the Mulliken symbol rules. The Mulliken symbol rules are that we assign the vector names, the irreducible vector names, an A or a B if the dimensionality is a 1. And dimensionality means the character under the identity, under E. So that first number that we by convention give it, we're going to have an A or a B. Now, how do we know if we have an A or a B? We give it an A if it's symmetric with the principal rotation axis. So for this first one, we are symmetric. We're a 1 with C4. That's our principal rotation axis. So we give it an A. The second one, we're anti-symmetric. We have a -1 under C4. So we give it a B. And then the Mulliken symbol rules tell us that for ones with a 2, dimensionality of 2, we call it E. And so at this point, our character table appears to be done. But if we're to look at this, we'll actually see that this is wrong. And the reason why this is wrong is because we're violating a rule here. We're violating two rules. One is, well, we only came up with we didn't come up with a gamma 4. Okay. But so that's a problem. And we could test a lot of different functions, and we actually wouldn't come up with any other functions that transform any differently. So you can think about xz or yz. Z doesn't help you because it's just multiplying by -1. Okay, so xz or yz are going to transform this b here. And you can do similar things with the quadratic function, with other quadratic functions. It's not going to help you. And so we don't have the right number of rows. We only have 3 rows, but we need 4 rows. Furthermore, if we remember the sum of the squares, one of the character table rules, if you look at my character table rule video, is that the sum of the squares of the dimensionality, in this case, we're going to be 1 squared plus 1 squared plus 2 squared, needs to equal the order of the point group, which is the number of operations. Here we have 1 operation in this class, 1 in this class, 1 in this class, 1 in this class. So we only have 4 operations. The order is 4. Well, those aren't equal to 1. And so we have a problem here. And the way we're going to rectify both of these problems is by getting into imaginary numbers. And what we're going to do is we're going to break up. And so I'm going to write in another color here, sort of the extension of this character table. But this is going to be our notes here on the top, because what we're going to do to this E vector, and our blue is going to be our correct E vector, is we're going to break up this E vector into 2 characters. These are sort of like subcomponents of this, and they're going to have imaginary components into it. It gets into some crazy math whenever you get into imaginary numbers. We're going to break this up, and we know the first components, the dimensionality of these are going to be 1. And so this E, I'm just going to cross out, but just keep it here so we can remember. And actually the real xy function is going to transform as this 2-part E vector. But now I have 1, 2, 3, 4 classes, and I have 1, 2, 3, 4 vectors. Okay, because we have a 2-part vector. And what we're going to do is, and we have now in our new system, our sum of our squares are dimensionalities, 1 squared plus 1 squared plus 1 squared, right? These 4 numbers equals our order of our point group, 1 plus 1 plus 1. So now we're back to satisfying the rules. The only thing we have to do is come up with these rather complicated imaginary values for this E vector. Okay, so how are we going to do that? Well, what we're going to do is we're going to give these letters right now. We're going to call them A, B, C. We're going to use placeholder variables to help us figure out what these are, and we're going to use the character table rules that we know of to help us derive what these values are. And so what we're going to do is we're going to take advantage of our other rules and also some special rules. There's a special rule for characters with these 2-part values that have for vectors with these 2 parts that have imaginary values. I call it special rule 5 in the character table rule video. But first, let's just go over our orthogonality rules. those apply for these components. So we know that, for example, any vector dotted with this vector has to be equal to 0. So 1, 1, 1, dotted with 1, A, B, C is going to be equal to 0. Okay? And so, and again, remember this has to be normalized when we're talking about the dot product. It has to be normalized with the number of operations in the class. I'm not going to write those ones anymore because all these are ones. So we just multiply one of these vectors by ones across the board. So it's going to be what I wrote. So if I multiply this out, I'm going to get 1 times 1, which is 1, plus 1 times A, plus 1 times B, plus 1 times C equals 0. And so that gives me sort of my first equation, which is A plus B plus C equals to -1. Now the exact same thing is going to be true for my second vector, part of the vector, because again, it has to be orthogonal there. Okay, and so we're going to get the same sort of math there. And so D plus E plus F is going to be equal to -1. And then we also know that the E vector components have to be orthogonal with B. And so we can write two further relationships, which is 1, comma, -1, comma, 1, comma, -1, dotted with 1, A, B, C, also has to be orthogonal. So that relationship is going to get us that 1 times 1 plus -1 times A, which is -A, plus 1 times B, plus -1 times C, which is -C, has to be equal to 0. So that's going to get me that -A plus B minus C is equal to -1. And the exact same relationship we can write. Again, the 1DEF vector has to be orthogonal, equals 0. And so by the same logic, we can write a very analogous equation. -D plus E minus F equals -1. And now at this point, there's some more, it becomes a huge system of equations, but there's other rules that we can use to help us. And so what are those rules? Well, one of the rules is that we broke this up, right, into components. So 1 plus 1 was equal to 2. And so A plus D here has to be equal to our original vector. This is why I kept it. So A plus D is equal to 0. Similarly, B plus E is going to equal to -2. And C plus F is going to be equal to 0. So we have all those relationships now, and so we can start just solving the system of equations. It's going to take a while, but here we have A plus B plus C equals -1. We also have -A plus B minus C equals -1. So both those equal to -1. So we'll set them equal to one another. A plus B plus C is going to be equal to -A plus B minus C. And this is going to be, then we can simplify this, right? 2A, move the A over, the B's are going to cancel. 2A's equal minus 2C, and A is going to equal to -C. Okay, and we can do a very similar thing with D plus E plus F and -D plus E minus F. They both equal to -1. So we'll set those equal to one another. And if we do that, I'll just write that out for clarity. We're going to get 2D equals -2F. And so D, we get something very analogous. D equals -F. So this is going to be the negative of itself. And this A and C's are going to be the negative of itself. We also, now that we know that A equals -C, we can plug that in for here, for our A plus D equation. And so that's going to say that -C plus D equals 0. And that tells us actually D equals C. And then we can do a very similar thing for C plus F if we plug, we can do the same thing for D equals negative F. If we plug that into A plus D, we're going to get A minus F equals 0, and so A equals F. And so at this point, we've really come a long way. And so we're going to go down here just to write some more relationships that we know. We know A plus B plus C equals -1. We know that A equals negative C, so I'm going to plug that in for A, and plus B plus C equals -1. Well, the C's canceled there, so now I figured out, B is -1. And so that's great, because now I can erase this B and actually put in black here. I'm going to change these to black. So these are now our real values here. I'm going to put in a -1. Okay, and I also know that B plus E equals -2. So that means since I know B equals -1, -1 plus E equals -2. That tells me E equals -1. So we can erase this and set this equal to -1. And so we're almost here. There's one more relationship we have to use. And again, this is special rule 5. And so I go over this rule in my character table video, character table rules video. But special rule 5 says that anytime you have these kind of subcomponents of a vector, when there's imaginary components and you're breaking them into two, the squares of the characters multiplied by the number of operations in each class equals 0. So so what I mean by that is we can square this vector, right? We have 1 comma A comma -1 comma C. So we can square all those components. 1 squared plus the sum of the squares plus A squared plus -1 squared plus C squared equals 0. And this will always be true if you multiply by the number of operations in each class. So in this case, it's just invisible ones, 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 ones here. But in other character tables, it will be different. So if we multiply all these by ones, this will always be true when you have these subcomponents here with these imaginary vectors. Where this comes from, it's a little bit different, but this is analogous to a rule where the sum of the squares normalized by the number of operations in each class equals the order of the point group. So to show you that rule as a reminder, if we took B, the B vector, we would take all the components, so 1 squared, -1 squared, and 1 squared, and -1 squared. And so that's 1, -1, 1, -1. And then again, normalize it by the number of operations in each class, 1, 1, 1. That's going to get you 4. And the reason why it's 4 is because it's order of the point group, the number of operations in the point group, 4, right? 1 plus 1 plus 1 plus 1. So, but special rule 5 says that, hey, for these individual components, it's not going to be equal to the order, it's going to be equal to 0, okay? That's just the mathematical construction of these character tables with imaginary components. So what this allows us to do is really figure out the last component of this. And the way that this works now is we have 1 plus A squared plus 1 plus C squared equals 0. And so that tells you now that A squared plus C squared equals -2, bringing those ones to the other side. But we know from earlier on that A equals just -C. Or in other words, C equals -A. So we can plug in -A and square it there. and that equals -2. So negative a squared, of course, is just a quantity to negative a squared is just a squared. So we're going to get a squared plus a squared, which is 2a squared, equals -2. 2a squared equals -2. That gets us a squared equals -1. That gets us, if we square root both sides, a equals square root of -1. And square root of -1, if you remember what that is the definition of I, the imaginary number, right? And so this is a relatively simple one with imaginary numbers in that we only have i's, negative i's. But then later you can have complex numbers where you have real and imaginary components. For example, I'm going to make a video on the C3 character table so you can see how that all works. It's just some more complicated math. So now I can erase all these. And so A is actually I, the imaginary number. Well, somewhere along the line here, we figured out A equals F. And so we know that if A equals I, F also must equal I. And then we also know that D equals -F, but let's see here. D equals -F. And so there we go. So I is F, and so D is going to be -I. And C, remember, was the negative of A, and A was I. So at this point, so that means that C is going to be -I as well. At this point, we are done. And it's good to just check this to make this make sense. Look, 1 plus 1 equals 2, I plus -I equals 0, -1 plus -1 equals -2, and -I plus I equals 0. And all these orthogonality rules and the special rule number 5 for these individual components will still be true. You can test this, let's say you could call this first component 1, comma, I, comma, -1, comma, -I. If you dotted that with A, 1, 1, 1, 1, you're going to get 1 plus I plus -1 plus -I. That's going to equal 0. So we're orthogonal. And so we can check that with something that's published, a published known character table, and you can see how they write this out. We basically derive this whole thing. We didn't talk about the rotation vectors, but those end up transforming identically to x comma y. I think that's sort of intuitive. We talked about xz, we didn't talk about that. I think I might have written. Did I write that down wrong? I think I wrote that down. Oh, I know what I did. When I was talking about xz here and yz, that was a small mistake. Sorry. Those are actually I was talking about xy times z. So it'll actually be xyz. The cubic function xyz is going to transform as b. Z is all at once. So anything times z is just going to be itself. So if xy is b, xyz is going to be b. But x and y transform as e. And so that was my mistake here. Xz and yz are going to transform as e. But other than that small mistake, we got everything correct here. And you can see there's 4 vectors here. The e consists of 2 components, and there's 4 to match the 4 columns, and everything's orthogonal.